So I'll begin. Are there questions?
Yeah, hello.
Yes, go ahead, please.
Hello. Yeah,
Uh,
sir.
I think the voice is getting cut.
Can you hear me now?
Yes, I can hear you.
Yeah, suppose in Green-Gordon field theory,
Yes.
if we trying to find out details like, say we have created a particle, some AP dagger 0.
Yes.
Details, probability of particle how do we?
Okay, again, your voice is getting cut. Can you repeat the question again?
Yes, what I am asking is in the KG field theory, suppose in the state AP dagger is acting on vacuum, if we try to find out the probability of finding the particle at some
Probability of finding the particle at some position x, is that what you're asking? Again, your voice got cut.
yes.
At position x.
Yes, that's what I'm-
Okay, yeah. So
yeah.
we have calculated the momentum eigenstates, right? Which is AP dagger on the vacuum, and you also saw that we have calculated the position eigenstates are given by psi dagger PR acting on the vacuum, right? Okay,
Yeah.
this was in the first homework exercise problem. So what we need to do is to take the overlap, the matrix element, inner product between these two, and take the mod square. Is that point clear? See, this procedure is the same. Suppose you have a state that is given to you, and you want to see what is the probability of measuring something else, right? You then go to the eigenstate of whatever you are trying to measure, in this case the position operator, and take the inner product of the eigenstate of the position operator with the state that is given to you, and take the mod square of that object. Is this clear? Again, either our internet connection is bad or yours is bad. Can anybody else hear me?
yeah.
Yes, sir. He got disconnected.
Okay. So maybe we'll come back to that question afterwards. Those two, we had some question.
Yeah. So I was saying that what we are doing right now, we are writing some quantum mechanical equation. Let's say the Klein-Gordon equation or the Schrodinger equation.
Yes.
We are writing it as a classical field theory by considering those wave functions as some fields.
Yes.
And by writing down the Hamiltonian, we are writing some A dagger A's and then defining a vacuum and sort of making a correspondence of that system of field with the particles.
Yes.
And also, according to what we did in the first two lectures, we see that those particles follow the equation of motions, like the Schrodinger equation or the Klein-Gordon equation, right?
Yes, that's right.
In the mechanics sense,
single
yeah.
particles. Okay.
Yeah,
Yes.
single particle equation, yeah.
Okay. Yes.
So with this mechanism, we can call any equation as a quantum mechanical equation in the sense that even for electric field,
yeah,
the Maxwell's equations are in principle classical.
Yes.
But if we do this process and identify those particles as photons or whatever, those equations themselves we'll call quantum mechanical.
Yeah, you could think of the Maxwell's equation as the analog of the Klein-Gordon equation for photons. That viewpoint is not very effective, but yeah, you can do that.
But like now there won't be any distinction between quantum mechanical and classical equations then.
No, the interpretation is different, right? When you are thinking of this as a field theory, you are thinking of this as purely classical field theory, right? Everything commutes with everything else.
Yeah.
and then you second quantize, right? And as you have seen, that gives not only single particle states, but multi-particle states back.
Yeah.
But the same second quantization also tells us that if we take the single particle state and try to write down a Schrodinger equation for the single particle states, you get back essentially the classical equation that you start with. At least at the level of the quadratic action, right? That's what you are seeing, right?
Yeah.
So, but the interpretation is different. That when you think of electromagnetic field equation as a classical field equation, right? Then there's nothing which do not commute with each other. Once you second quantize it, right, and then focus on the single particle states, then it looks like that the wave function of the single particle states follow the same equation that we started with, the classical equations.
Yeah, and this we can do for any classical equation that we have.
Yes, so given any classical field equation, you can quantize it. You may not get something sensible at the end, right? But in principle, given any classical field theory, you can quantize it. Does that answer your question?
Yeah, I mean, it's fine if it's that way.
Yeah, I mean, the point is, as I said, it's not necessary that you will get a sensible answer every time.
Yeah.
But you can certainly try to quantize it, given the classical field theory. Any other question?
Sir?
Yes.
So, given that, so if our field is such that it and on the boundary it is going to 0,
Yes.
then we cannot have terms like 1/phi in the Lagrangian, because then the action will become infinite.
Yes. So normally we talk about actions which are polynomial in phi. If you have
Okay.
1 over phi, right, you certainly cannot quantize it by the standard perturbative method.
Okay. So, like, because in classical mechanics we have 1/r potential, but here we cannot have that
Yeah,
type
so
of.
normally in quantum field theories of this kind, you don't have 1 over phi kind of potential. You can imagine that you have something like 1 over phi square plus a square.
Oh, okay.
And
So that we can expand in phi.
Yeah, you can expand in phi and then try to quantize it that way.
Okay. So our boundary condition will dictate what type of terms we can have in the Lagrangian.
Well, not boundary condition. The boundary, there are certain, as I said, not every field theory that you can write down is sensible, right? It doesn't have a sensible quantization.
Okay.
If you start with something like 1 over phi, then that doesn't seem to have sensible quantization, but maybe you can try to see if you can redefine phi as 1 over phi, right? And try to get a sensible theory out of it. Right? I mean, instead of 1 over phi, suppose you define chi as 1 over phi and write the Lagrangian in terms of chi. You can ask, can you quantize in terms of chi?
But then del mu phi will have a 1 over chi square something.
Yeah,
like that.
unless del mu phi also had a 1 over phi to begin with.
Oh, okay.
Right. So sometimes you may get the Lagrangian or the action in a form which looks bad, but by change of variables, you can make it look good. But it's not always possible.
Okay.
Any other question?
Hello.
Hello, yes.
Sir, as you said that the integral of J0 is conserved. But sir, I don't understand the meaning of the number operator is a consequence of phase symmetry. Sir, physically, I'm not understanding this sentence.
Okay, so the statement is that we have a phase symmetry, right? For the Schrodinger equation, we had a phase symmetry under which you change psi to the I theta times psi.
Yeah, and I understand, sir.
Yeah, and so corresponding to that, there is a conserved charge, conserved quantity. And what we found is that that conserved quantity is integral of psi star psi. And in quantum theory, that becomes integral of psi dagger psi. And now what I'm saying is we have seen independently earlier that integral psi dagger psi is the number operator. Right? In Schrodinger system, we identified the number operator as sum over n, a n dagger n, right? Which we saw in the second quantized language is the same as integral psi dagger psi. So all you are saying here is that the same number operator that we had introduced earlier now can be interpreted as the conserved charge correspond to the phase.
Okay. Yes, sir.
Is that okay? That we started with the phase symmetry, we got a conserved charge, and then it's an observation that that conserved charge quantity is the same as the number operator.
Okay. Yes, sir.
But it's not that from the beginning you could have known, right? Of course, now with experience you may know, afterwards, right, in other systems. But if somebody gives you a symmetry, a priori you may not know what conserved quantity will reflect, what will be the physical interpretation of the conserved quantity. All you know is that the Lorentz procedure tells you how to construct a conserved quantity. And here you recognize that conserved quantity as something physical, the number operator.
Okay. Yes, sir. So,
Yes.
sir, one more doubt. Sir, in a capital P expression, sir, the integral of dqp small pi. Sir, small pi is a individual momentum of the particle in the expression of capital Pi.
Let me go back.
Yes, sir. This.
Yeah. So
Sir,
that's the level. Integration variable.
Sir, small pi is just a label or the individual momentum of the particle.
In this, it's just a level, right? When you have written it as an integral, see, this is an integration variable, right? I could have replaced p by u, right? But once you have this expression, right? Now you look at this action on this state. And what we see is that when capital Pi acts on this state, you get something like sum over Pi's of the same state. Now these tells us that as if it's some quantity that is adding for individual particles, right? Suppose you didn't know that it's momentum, but you observe that there is some attribute. I mean, this whatever the eigenvalue of P hat I is, it's as if individual particles carry that charge, that quantity, and the total quantity is sum of all the n particles. Then you also see that the energy, right, has a similar form with the quantities being EP. And then you also know that EP is given by square root of P square plus M square, right? That we have seen already. That's the definition of EP. So then you can say that it's as if this state represents a state of a particle, of n particles, of momentum P onto Pn and energy EP onto Epn. So this interpretation you have to see. I mean, if you didn't know anything about quantum field theory, all you know is the eigenvalues, these operators and their eigenvalues. Okay, a priori nobody tells you that this is momentum, this is energy. Okay, this is energy because this is Hamiltonian. Energy is always defined that way, but a priori nobody told you that this is momentum. But now by comparing this with what you know from everyday experience, that the particle, if you have n particle system, n free particles, then the total energy is given by the sum of the energies of individual particles, and the total momentum is given by the sum of the momentum of individual particles, and that for each particle the energy momentum relation is E equal to square root of P square plus M square. Using that, you can say that it's as if this state has an interpretation of a state of n particles carrying momentum P onto P. And then that tells us that capital P hat I will be interpreted as the ith component of the total.
Okay. Yes, sir. Okay.
That's clear. So in this expression, this is just a label. The interpretation of this as a momentum, the momentum here, of course, these characterize the state, right? So these are the physical moments.
Okay. Yes, sir. Understand, sir. Okay. Thank you, sir.
Any other question?
Hello, sir. So I have a question.
Yes.
So for
Sorry.
to represent the free particles, we require KG field theory or Schrodinger field theory, because we use kg quantum field of the action to get the single or multi free particle state, but the field have classical Schrodinger, but that field satisfy quantum field satisfy the classical Schrodinger equation.
Okay, in this case, it satisfies not classical Schrodinger equation, but classical Klein-Gordon equation, right? See, earlier you had, so both Schrodinger system and the Klein-Gordon system describe a system of free particles, but in the Schrodinger case, it's a system of non-relativistic particles, okay? Possibly moving under a potential. In this case, what we see is that it describes a system of relativistic particles, because the energy relation between energy and momentum that we have is this, right? That's the relation that we have for a relativistic particle. Whereas for the Schrodinger system, the ENs that we had, the energy eigenvalues, those are the energy eigenvalues of the non-relativistic Hamiltonian. So both describe a system of free particles, okay? Free meaning mutually non-interacting particles. But in one case, it's non-relativistic particles. In this case, it's relativistic particles. Is this clear? Okay, I think your voice is getting cut, but I'm assuming it's okay, and I'll you can ask afterwards. Any other question? Okay, so if not, let me then begin. So let me remind you what we did last time. So we are analyzing the conserved quantities in the Klein-Gordon field. And we consider the conserved quantities associated with translation symmetry. So translation symmetry, let me remind you, takes this form for infinitesimal translation. Phi tilde of x is a transformed field. It's phi of x plus epsilon. And because we are working first order in epsilon, we expanded it in Taylor series expansion in epsilon and wrote it this way. Here, because this is Lorentz index and it gets repeated twice, sum over rho is implied, right? So rho is summed over from 0, 1, 2, 3. These epsilon rows are 4 parameters describing time translation and the space translations. We are also seeing that this is the same. Okay, we also analyze this. The Lagrangian density in for this new field configuration, which is given here. Here, this is the substitution of phi tilde x by phi of x plus epsilon. And then we said that, okay, here again, we see that effectively all the x's inside the Lagrangian density has been replaced by x plus epsilon. So you can do a Taylor series expansion of this as well. So you get the original Lagrangian density and then epsilon rho del rho times the Lagrangian density, higher order terms I'm. Then we compared this with the general set of transform definitions that we had given. And here I remind you that we are trying to do this analysis for all 4 epsilons at one go. Okay, otherwise you have to do it one by one. So if you want to do all 4 epsilons by one, all 4 epsilons at one go, we write it as epsilon rho chi rho, sum over rho implied. So this was the definition of chi rho. Okay, how much phi tilde differs from phi to first order in epsilon, and the definition of k mu rho was given by how much L differs, L of phi tilde differs from L of phi. And we had argued on general grounds that if this is a symmetry, then it better change by total derivative. And whatever total derivative it is, we had called it k. So because you have this extra rho, which I write it as del mu k mu rho. And then what we did was we compared these general definitions of chi rho and k mu rho with the explicit forms that we had found here. This is specific translation. And we saw that we can identify chi rho as del rho phi because we compared this with this equation over here. So chi rho is del rho phi. And then comparing this with this over here, we saw that k mu rho is given by L times delta mu rho. This delta mu rho reflects the fact that here you have a derivative with respect to mu, here you have derivative with respect to rho. So if you have a delta mu rho in the expression for k mu rho, that converts del del x mu to del del x rho. Okay, so that's what Here it is. And using these, we constructed the conserved current associated with transmission along the rho direction. So this again was general formula, J mu rho. Okay. General formula didn't have rho, but here you have the rho because we have one for every epsilon, every component of epsilon. So this was a general expression. And then we substituted for chi rho, what we have here, del rho phi. And we substituted for k mu rho, what we have here, L times delta mu rho, and we arrived at this expression. And this we called as a component of the energy momentum tensor T mu rho. Okay, so I have written mu up, rho down. Then we also defined the T mu rho both index up simply by multiplying raising rho by theta, by the Amin constant. So we are going to use this, but are there any questions for what we did? Is this clear to everybody? The derivation of energy momentum tensor?
Sir,
Yes. Go ahead.
can we have T mu rho is like in first term plus, in second term minus?
Well, you can define it that way, right? But that will not agree, for example, with the usual definition of energy. Suppose you have T apart 0, 0, right? We saw that the integral of that gives the usual Hamiltonian. If you
Yes.
define it with just change sign, right? It will give you minus h.
Yes.
So it's just a convention. See, if you change the overall sign, right, it will still remain conserved. Right? So there's a confusion about it not being conserved. It's just that it's convention to define P mu rho this way.
Okay.
Yeah, but you can certainly change the overall sign. Is this okay?
Okay, sir. Okay.
Any other question? Okay. Now here there is one point I want to emphasize, okay, which I didn't emphasize last time, but we are going to make use of this today. That up to this point, we did not really need explicit form of L, okay, because you see the whole derivation is on this page, right? So we used, of course, the fact that the L is invariant, right? But as long as L is invariant, we don't need explicit form of L because you have not used the explicit form of the Klein-Gordon Lagrangian anywhere so far. Of course, in what we did last time, we then used in this expression the fact that L is the Klein-Gordon Lagrangian, explicitly computed this, yeah, and found the expression for the energy momentum tensor. But up to this point, any L is good enough. And the second point I want to emphasize is that up to this point, the analysis will also hold for multiple fields. Right? If you had multiple fields, for example, all that will change is that here you have, in the first term, you have a sum over I. Okay. Here there will be I, and here there will be an I. Because every field has its associated chi I, right, which will have del rho of phi I. Okay, and we will get the expression with sum over I included. So we'll continue to use single scalar, but we should keep this in mind because later on when you say that it also holds for multiple scalars, you should know why it works, right? Because whatever you have done could have been done for multiple scalar fields as long as the Lagrangian is invariant by replacing this by sum over I. Is this clear to everybody?
Sir,
Yes.
sir, I have a question.
Yes.
So you just said that the Lagrangian is invariant under these this transformation. So are you claiming that because it's a scalar? Or
Yes. So invariant only in this sense, right? That L phi tilde of del mu phi tilde is L of phi del mu phi. Okay. Lagrangian density changes like this under translation. So this doesn't require that it's a scalar. The phi's are scalars. Of course, if the Lagrangian has explicit x dependence, okay, then this is not true. Then translation is not a symmetry. And then, of course, there's a conserved charge. But if
yeah, because yes.
We have already assumed that the Lagrangian is translation invariant. Once you assume that the Lagrangian is translation invariant, then this is the structure.
Okay, sir.
okay?
Sir,
Yes.
so in the expression, wherever this del rho of L is appearing,
Del rho of L is appearing, yes.
so we are taking the implicit dependence of X into account here.
Yes. See here, what we have said is that the Lagrangian phi, the X dependence is to the argument of phi, right? Because we know that the phi, we started with this, right? Then we replace phi tilde by phi of X plus epsilon. If the Lagrangian had some implicit dependence on X, like X squared, that will not be replaced by X plus epsilon squared, right? So then this is not a symmetry.
Okay, okay.
So then you cannot write it this way, right? Because then this one will act also on that X squared that is sitting inside the Lagrangian density.
Oh, so this is written as a partial derivative, but it acts like a total derivative because it is acting also on phi and on explicit dependence.
Well, if it acts on the explicit dependence, right? What I'm saying, then this is not an identity.
Oh, yes.
Right? Yeah. So here, okay, here I have written it as partial derivative because there are four coordinates, right?
Yes, yes.
Right. That's why it's a partial derivative. But it acts on all the X dependencies inside, right?
Okay, okay.
Okay. So this derivation works only if there is an explicit X dependence in the Lagrangian density. Otherwise, it will not be true.
Okay.
Okay. So now we are going to start to a new quantity or a new symmetry. That's a Lorentz invariance. So we'll be studying Lorentz invariance of the Klein-Gordon action. You might expect that the system has Lorentz invariance, but we will make it more explicit because the equation looks Lorentz invariant. Okay, but we will make it more explicit in what sense it is Lorentz invariant, and then you will find a concept charge. So that Lorentz transformation law for the Klein-Gordon field is given here. Phi tilde of X is simply phi of lambda X. What is lambda? Lambda is a Lorentz transformation matrix. So here I have written in components lambda X, the mu component of lambda X. See here, X is a 4-component vector, lambda X better be 4-component vector. So the muth component of lambda X is given by this sum over here. Sum over nu is implied because it's repeated. And lambda, this matrix lambda satisfies lambda eta lambda transpose equal to eta. You may have encountered this matrix from the Lorentz transformation, but this is exactly what a Lorentz transformation matrix does. So in components, this can be written in this way. Lambda rho mu, eta mu nu, lambda sigma nu is equal to eta rho sigma. The fact that you have written one index up, one index down, it's at this stage a matter of convention, but it's a useful convention because by writing it this way, we can make sure that whenever you have repeated index of this kind, you always have one up, one down. Okay, and that makes the proof of Lorentz invariance explicit. But we'll of course prove it explicitly. Okay, we'll not assume that once you have one up, one down index, it's automatically Lorentz invariant. So this is the component form. Okay, so let me explain this. So lambda, eta, lambda transpose. So you think of lambda as a matrix with mu as the row index, nu as the column index. Even though one is up, one is down, you think of the first index as row index, second index as column index as a matrix. And it is in this sense that I have written this equation. So let's see in the component form if it agrees. So lambda rho mu, because it's lambda times eta, the row index, the column index of lambda should match with the row index of eta. Okay, so mu here, mu here. Then the column index of nu should match the row index of lambda transpose. But the row index of lambda transpose is the same as column index of lambda, right? Because lambda is transposed. So that's why it have lambda sigma nu. Okay? Nu is the column index. In the transpose form, nu is the row index, sigma is the column index. And on this side, of course, you have eta, so that I have written as eta rho sigma. So this is a component form of the constraint that the Lorentz transformation matrix has to satisfy. Is this clear? I'm sure that you have seen Lorentz transformation before. It's just that this particular notation you may not have encountered before. So if there is anything confusing, please ask.
So, one question, sir.
Yes.
So isn't it the condition that phi tilde x equal to phi lambda x? Isn't it a much stronger demand than that we are having before? That the Lagrangian will be differing by a complete definite integral.
Yeah. Okay. So we have not come to Lagrangian yet, right? So here you are claiming, right, that if we define this transformation, this will be a symmetry of the Lagrangian. So we can take any transformation, right, and check if it's a symmetry.
Okay.
This is a symmetry yet, right? You have to check this. If it fails, if it is not true, then that means it's not a symmetry. Then maybe we should try something else. So right now we are simply saying that let's define the Lorentz transformation of a field this way, and we'll now go ahead and check if it actually leaves the Lagrangian invariant or the action invariant.
Okay.
So this is like we declare that translation means you change x to x plus epsilon in the argument of phi, right? So this is the analog of that. That we are saying Lorentz transformation means you change x to lambda x in the argument of phi. Okay, so you are now going to check that this is a symmetry of the time invariant action, right? Otherwise, you can throw this away, right? Otherwise, it's not of much use. You either have to throw at this transformation or you have to throw at the Lagrangian, right? If you want this to be the symmetry. So let's check what happens. So the Lagrangian, so you have to check if this is related to L of phi, del mu phi, by a is equal, okay, or is related by total derivative. So we take L of phi tilde x, del mu phi tilde x. We transform. So at this stage, all you have done is that you have taken the original Klein-Gordon Lagrangian and substituted phi by phi tilde. So now we use the definition of phi tilde. Phi tilde x is phi of lambda x. So you substitute here phi of lambda x. This of course remains as ordinary derivatives, right? Because they are derivative with respect to x. This point is clear, right? I have not really done much. I'm trying to compute this, right? And I'm trying to check if the action is invariant, because after you compute this, you have to integrate over x. That's the action, right? And the action should be invariant. So now we are going to define x prime as lambda rho sigma x sigma. This is our choice, right? We just define a new variable. After all, eventually x will be integrated over, right? So it's just a label. So we define x prime rho as lambda rho sigma x sigma. And the idea is that we will try to rewrite this whole thing in terms of x prime. Okay, and we will see that that will help us in proving that the action is invariant under this transformation. So if we define x prime this way, now this becomes simple. Lambda x I can replace by phi of x prime. But this is still derivative with respect to x, right? So you have to convert this somehow to derivative with respect to x prime if we want to try to bring the thing in the original form. So that can be done by chain rule. So partial mu is by definition the derivative with respect to x mu. But now by using chain rule, I can write this as the derivative of x prime with respect to x mu and then del x prime. Okay, this is just a chain rule. And now we use this relation to write this as lambda rho mu del prime rho. Is this clear? Okay, maybe let me go ahead and then the motivation will become clear. So here we start from here, this expression over here, and write lambda x equal to x prime. Okay, that's
So,
yes.
sir, phi in the Lagrangian density, then phi tilde x is also replaced by x dash in
No.
the expression.
What is the definition of phi tilde x? phi of lambda x, right? Okay. So Lagrangian density is here. Yeah, you could have written this as phi of lambda x. Okay. But we want to check that this, see, or the original, what do you have to check? Let me go one step ahead. So what do you have to check? We have to check that S of phi tilde, which is given by this,
Okay.
is S of phi, right?
Yes, sir.
So left hand side, you want to keep it this way.
Okay.
Right? We don't want to change x by lambda x here, because on the left hand side, we have integral d for x, L of phi tilde x, del nu phi tilde x, right? We have to show that this is the same as S of phi.
Okay, sir.
Is this clear?
Yes, sir.
Okay. That's why we are keeping this as it is, L of phi tilde x, del nu phi tilde x. And we are using this expression for this, for in the specific context of Klein-Gordon Lagrangian, or Klein-Gordon Lagrangian density. To rewrite this as, so what did we find? So del mu phi will be lambda rho mu del prime rho phi. Right? That's what you have written here. In the argument of phi, lambda x have replaced by x prime. Then here you have del nu phi. That will be lambda sigma nu del prime sigma phi x prime. Right? Just replace mu by nu and rho by sigma in this expression. That will be lambda sigma nu del prime sigma phi x prime. This remains as it is, except the lambda x has been replaced by x prime. And now we use the fact that this eta mu nu, lambda rho mu, lambda sigma nu is eta rho sigma. This equation. So because lambda is a Lorentz transformation, provided it satisfies this equation. So you replace this combination by eta rho sigma. And you see that it becomes minus half eta rho sigma del prime rho phi x prime, del prime sigma phi x prime minus half m square phi x prime square. And that means that this is the same as the Lagrangian density evaluated at phi of x prime and del prime nu of phi x. Right? Because all we have done is that on the original Klein-Gordon Lagrangian, phi x has been replaced by phi x prime, and all the derivatives with respect to x has been replaced by derivative with respect to x prime. That's what we mean by this. Is this point clear? Any confusion here? What you are trying to show? So this is an identity, provided you write x prime as lambda rho sigma x sigma. And furthermore, Lorentz transformation matrix has determinant of lambda equal to 1. That you can see easily by taking the determinant on both sides. Determinant of lambda transpose is the same as determinant of lambda. So on the left hand side, you have determinant of eta, which is minus 1, times determinant of lambda square. On the right hand side, you have determinant of eta, which is minus 1. So you get determinant lambda whole square is 1. So mod of determinant lambda is 1. So this tells us that when you change variable from x to x prime, d for x prime will be the same as d for x. So this is an identity that we found, and now we are trying to use this identity to show that the Klein-Gordon action is Lorentz invariant. So let me give the derivation, which is just one line now. So these are the two identities we have found. This is equal to L of phi x prime del prime nu phi x prime, and d for x equal to d for x prime. Of course, this makes sense only if I tell you what x prime is, which is here. And so now you start with s of phi tilde, which is here. Right? Just replace phi by phi tilde. Then using this identity and the fact that d for x equal to d for x prime, we can rewrite this as the integral d for x prime, L of phi x prime del prime nu of phi x prime. But now, of course, x prime is just a dummy variable, right? It's just an integration variable. We can change the name from x prime to x. Phi tildes have become phi, right? That's the important thing. So you can change x prime to x in this, and that gives us back x of phi. So this is what establishes that Lorentz transformation is actually symmetry of the Klein-Gordon action. Is this clear? Any confusion here?
Sir, so given a action, can we is there any procedure to find out what symmetries it has, or we have to guess?
Well, if the symmetry is very complicated, you have to guess. I mean, there's no fully systematic procedure that if somebody gives an action, right, that you follow this procedure and you will find all the symmetries. Some symmetries are, of course, familiar, right? So those you can check. But there may be unfamiliar symmetries which will be hard to guess. You have to find by trial and error.
So how can we be sure that we have found out all the symmetries of the action?
Well, you may not be sure, right? But you can still work with it, right? You can find the physical quantities, right? See, symmetries help us organize things, right? Symmetries help us in doing things simpler. If you haven't found some symmetry which exists, right, then maybe you cannot do things very simply, right? You cannot make use of that symmetry, but you can still do it the hard way. See, after all, given the Klein-Gordon field theory, right, we found a particle spectrum, right? And in fact, we can do, I mean, at a level of free Klein-Gordon field theory, right? Anything that you'll be doing, you can do without using symmetries. So symmetries are useful, but they are not necessary for solving a theory. Is this point clear?
Sir, we are always looking for the symmetries by guessing, right? I mean, without any manipulation or something. By looking at Lagrangian, always.
See, the point is, physics is not always that there are well-defined set of rules and you manipulate and you get the result that you will get, right?
Yeah.
Otherwise, there will be no research, right? So often you have to guess, and of course you can guess, but then at the end you have to check, right?
Yeah.
So there are many Lagrangians which have very complicated symmetries, and it took people many years to figure out that they have that symmetry. Right? So it's not as I said, an algorithmic process that you start with a Lagrangian and you do this, and you find all the symmetries.
Yeah, yeah.
But the point is that given a Lagrangian, even if you haven't found all the symmetries, you can still analyze it. Right? Is that if you have the symmetries, you will see many more patterns which are hard, which will look accidental otherwise.
Okay.
Right? I mean, even in hydrogen atom, for example, right? When you solve hydrogen atom, right? You see the rotational symmetry easily, but that doesn't explain many degeneracies which are actually there in hydrogen atom.
Yes.
Right? Which you discover afterward that there is a bigger symmetry, right? Which the theory, which the hydrogen atom problem has. If you don't use it, you can still discover, calculate the spectrum, you can find the degeneracies, right? Is that you will not know why they are degenerate, why their energy levels are degenerate, where symmetry doesn't tell us that they should be degenerate.
Yeah.
So it's like that also in quantum field theory, right? If you haven't found certain symmetries, doesn't mean that you have to stop working, right? You can still work with the quantum field theory, analyze it. But if you find the symmetry, you will see the pattern, right? There were some patterns which may look strange otherwise, but symmetries will explain it.
Yes, okay. Thank you, sir.
Any other question?
Sir?
Yes.
So the action you have just written.
Yes.
Here the in the left hand side, the Lagrangian is a function of phi tilde.
Yes.
So phi tilde is a different field than phi.
Well, but phi tilde is defined here.
Yeah, it is defined, but it's not the same field.
No, phi tilde of x is defined as phi of lambda x.
I mean, sir, that yes.
Yes.
So I mean that if we take phi tilde x and if we take phi of x, then they will not be same.
No, they will not be the same.
Yeah, phi tilde x is same because x has a Lorentz transformation.
No, phi tilde x is not the same as phi of x. Right? As a function, they are different. Phi tilde x is defined as phi of lambda x, right?
Right.
Okay. So phi tilde at a given point is not the same as phi at the same point.
Yes.
So the point is that what is the point here? That we have given phi of x. Okay. We can evaluate the action. It's a number. Now I am telling you that instead of giving phi of x, I give a new function, okay, which is phi of lambda x. Call this phi tilde x, and then you substitute this new function in the action. In general, you will get a different action, right? Different number. We call that this is a symmetry when the new number is the same as the old number. And this has to be true not just for one given phi of x, for any function phi of x that is given to you. It has to happen that when you replace phi of x by phi tilde of x, as that is phi of lambda x, you should get by the same action. So phi tilde x is a defined function, but is determined in terms of phi. Because otherwise this equation doesn't make sense, right? If phi tilde is a totally independent function, right, then what do you mean by this is the same as this? So the claim is that if phi tilde, the new set of functions phi tilde are related to the old set of functions phi, or the old function phi, by this particular rule that phi tilde of x is phi of lambda x, then the analysis that we did, the manipulation that we did, shows that the action evaluated at phi tilde is the same as action evaluated at phi.
Okay, sir. Thank you.
Any other question? Is it clear to everybody? Okay, so let me proceed. Okay, so now that we have identified a symmetry, we'll try to construct the associated conserved quantity. And as usual, to find a conserved quantity, you have to find the infinitesimal version of Lorentz transformation. So let's do that. So we write lambda as identity matrix times epsilon times omega, because identity transformation is the identity matrix. So you take a small number epsilon times some matrix omega, right? We'll find what omega is soon. In components, this means that the matrix, the lambda mu nu, we are taking it as delta mu nu because this is the identity matrix, plus epsilon times omega mu. And again, when you think of this as a matrix, you think of the first index, okay, the index that is left as the column, as a row index, the second index as a column index, right? When you think of this as a matrix. Now, we examine the consequence of this lambda eta lambda transpose equal to eta. Okay, this is a condition that Lorentz transformation matrix has to satisfy. So we write this I plus epsilon omega eta I plus epsilon omega transposed as eta. And then now we expand both sides, keeping terms up to order epsilon. Okay, because epsilon is taken to be infinitesimal, so order epsilon square terms you can ignore. So you see that the leading term, right, the epsilon independent term cancels because there is eta on the right hand side and eta on the left hand side, because you get I identity matrix times eta times I, that's eta. Then the order epsilon term, there are two terms of that kind. So one is omega times eta times identity, that is omega times eta. And the other one is identity times eta times omega transpose, that's eta times omega transpose. So this must vanish, right? Because this is the only combination to order epsilon. So this combination must be 0. That means that omega eta plus eta omega transpose should be 0. And here I have rewritten in the components omega mu rho eta rho nu plus eta mu rho omega nu rho equal to 0. Why is it nu rho? Because it's omega transpose, right? So you have to transpose the matrix, so the row column index of eta has to go with the column index of rho. And now you can rewrite this as omega upper mu nu plus omega nu mu equal to 0. Where omega upper mu nu we have defined by the standard rule, right? As I said, raising and lowering is always done by eta. So omega upper mu nu by definition is omega mu rho times eta rho. So you see that this term becomes omega mu nu, right? Because the second index has been raised. And this term becomes omega nu mu, right? Because again the second index has been raised, right? And second index has been raised to mu. So that gives this equation. Are there questions? Is it okay with everybody?
Sir, I have one question.
Yes.
So in the definition of new field, so can you go to the previous page?
Yes. Phi tilde.
Yeah. So there in the argument of phi tilde,
yes,
shouldn't it be x prime? So no, the previous page of the,
yeah.
Yeah, here in the first line, phi tilde of x prime, because
Yeah,
it's
but okay, at this stage you have not defined x prime, right? But if you define x prime as lambda x, as we have done already afterwards, then this will tell us phi tilde of lambda x is phi of lambda x, right? That means phi tilde is the same as phi. That's not what we want, right? Then that's not no transformation at all.
oh yes, yes.
Right? So you can put only lambda on one side, right? Not on both sides.
So it's the coordinates, they are not getting transformed, right? Just the field is getting.
Yeah, so transformation is always best to think in terms of fields, right? That we take one field configuration, it transforms to a new field configuration, right?
Okay.
That may be induced as if the coordinate is transformed, right? But when you have a quantum field theory, it's best to think of all transformations as acting on fields. That a transformation means that given a field configuration, which means a function of space and time, okay? A transformation is a rule that generates a new function of space and time. So we are given a function phi of x. That means we know phi at all points in space and time. How do you construct the new function phi tilde? By this rule, right? That we evaluate the old function but not at x, at lambda x, and we call that phi tilde at the point x. Is this point clear?
Okay, yes.
So in quantum field theory, always think of the transformation as on fields. Now this may sound somewhat counterintuitive because in quantum mechanics or in classical mechanics, you think of the fields as acting on coordinates, right? But you remember that in quantum mechanics or classical mechanics, the coordinates are the dynamical variables. That's why fields act on those. In quantum field theory, the dynamical variables are the fields, right? Not the coordinates. Coordinates are just labels. So a transformation should take one field configuration to another field configuration, and that's what it is.
Okay.
Yes.
Sir, when we construct the conserved quantity correspondence to the transformation, so sir, is it necessary that the symmetry of the action must be continuous or discrete?
Yes. So the point is the Lorentz theorem refers to continuous, right?
Yes,
and
sir.
that's what we have defined so far, right?
Okay.
For discrete symmetries, there are other consequences, but there are no conserved charges of the kind that we have found, which can be written as integrals of some density. So we'll come to discrete symmetries afterwards, but at this stage, we are talking about continuous symmetries. And the Lorentz procedure certainly requires continuous symmetry, right? Because otherwise there will be no infinitesimal horse.
Yes, sir.
And those exist for continuous symmetries.
Okay, sir. Okay, sir.
Any other question? Okay. Okay. So where were we here? Okay. So what we see from here, this relation is that omega, once you raise both index up, omega mu is an antisymmetric matrix. And in fact, it can be an arbitrary antisymmetric matrix because that's the only condition that we get, right? For any arbitrary antisymmetric matrix that you choose, right, which satisfies this. Once you construct this transformation I plus epsilon omega, it will satisfy this equation, right? That's the condition for Lorentz invariance. So it goes both ways. An infinitesimal Lorentz transformation is associated with an arbitrary antisymmetric matrix. Or you can say, if somebody gives you an arbitrary antisymmetric matrix, 4x4 antisymmetric matrix, you can construct an infinitesimal Lorentz transformation. By first, of course, you have to construct omega mu rho, right? One index has to be lowered by eta. And then you construct this combination I plus epsilon omega, and that is guaranteed to be Lorentz transformation matrix. And if this is antisymmetric, we'll also often use this omega with 2 lower index. That just corresponds to lowering both indices by eta. This is also antisymmetric. So this we can easily verify. So a 4x4 antisymmetric matrix has 6 independent parameters, right? 4C3, that's 6 independent parameters. And those 6 independent parameters, in fact, are familiar. There are 3 boosts, right? Lorentz transformation contains 3 boosts and 3 rotations. Okay. So these 6 independent parameters are the 6 infinitesimal versions of the boost transformation and the rotation transformation. And our goal will be to find the conserved charges associated with Lorentz transformation. Is this clear? Are there questions? Because once you have constructed an infinitesimal symmetry, right, we can apply Noether's procedure, and that's exactly what we are going to do. But what we need to do for this, for applying Noether's procedure, is that you have to construct the analog of the chi-i's and the k-mu's, right, that we introduced. And you have to do this for each of these 6 independent infinitesimal transformations. Where you see, we expect 6 different conservation laws, right? Because there are 6 parameters, 3 boosts and 3 rotations, okay, or encoded in this omega. And as in the case of translation, right, where we dealt with all 4 of them at one go, here also we'll do all together, do it all together, right? Instead of having to find 6, instead of having to repeat this analysis 6 times, right? One for every independent omega, okay, we'll try to do it all together. And for this, the way we'll do it is slightly different from what we did for Lorentz symmetry. That here, right, we'll just keep omega as an arbitrary matrix, right, and we'll work with a transformation of this kind, right, and see what the conserved Noether charges. And that will be conserved for every omega, because for any omega that is antisymmetric, when both indices raised or both indices lowered, gives an infinitesimal Lorentz symmetry. Are there questions? Okay, so let me proceed. Okay, so let's recall that we have proved this for Klein-Gordon action. But this is also the general requirement of Lorentz invariance. Okay? That under Lorentz transformation, we say that it will be an invariance provided L remains unchanged. And we are dealing right now. We are dealing with scalar fields, okay, which transform. So scalar fields, let me remind you. Let me not remind you. Let me tell you, are the ones which transform this way. Okay, later on we will see that there are other fields of this kind. So we call a field a scalar field if its Lorentz transformation not takes this form. Okay, we'll see that there are other kinds of fields whose Lorentz transformation is not of this kind of this form. Okay, so you had this relation, and now let's look at infinitesimal transformation and see what happens. So you have defined this x prime, right? Lambda mu nu x nu, right? It's only for that x prime that this is true. Now we are using lambda mu nu to be infinitesimal, so that's delta mu nu plus epsilon omega mu nu x nu. And now after you do this contraction, the first term is x mu, and you get epsilon times omega mu nu x nu. Okay, again, sum over nu is implied, right? Because nu is repeated in x. So using this, right, and using this equation, you can see that L of phi tilde and L nu phi tilde is given by L with x prime in its argument replaced by this. So that basically means that we can get the result by simply Taylor series expanding L in powers of x prime, okay, because the x prime differs from x by small amount. So we can write this as L of phi x del nu phi x plus epsilon omega mu nu x nu del mu of x, right? Because this is the change in x mu, right? As you can see, this is the change in x mu, and we are taking derivative with respect to x mu of L, and of course sum over mu and nu are implied in this. Okay, is this clear? We are doing this because we have to find k mu, right? And k mu, if you recall, is related to the difference between these two, right? To construct k mu, we have to calculate the difference and write it as a total divergence, del mu k mu. Right? That's what we are trying to do. But here we see that we are more or less there. Okay, there's a del mu which has appeared here, but somehow there's an x nu sitting outside. Okay, that looks problematic. But now we claim that this same expression, that is there on the right hand side, can be written by pulling the del mu outside the whole thing. Okay, so the difference between this and this, either you have this partial derivative sitting outside the whole expression. Yes. Any question? Now, of course, we have to check that this is true, right? This is not the same as this in general. But what is the extra term? Right? Suppose you try to calculate this, the extra term that you will get this, of course, right? But the extra term will be when the derivative acts on x3. That's delta mu, right? Del del x mu of x2 is delta mu nu. So let's see what to get there. So you'll get an extra term, omega mu nu del mu x nu. That's omega mu nu delta nu mu. Now with some manipulation, this I'll write as omega mu rho times eta rho mu, right? Because we can always raise the index and multiply by eta rho mu. Then this contraction gives you back eta rho mu, right? Because that just sets mu equal to mu in this expression. And now we see that omega is antisymmetric, eta is symmetric. So after you sum over mu and rho, you get 0. Okay, because a symmetric matrix times an antisymmetric matrix will give you 0, because once you exchange mu and rho, right, this remains unchanged, this changes sign. So they just cancel pairwise. So what this shows is that this quantity here is indeed the same as this. Is this clear? So this we are going to make use of.
So del mu won't act on omega.
No, omega is a constant matrix, right?
Why?
Because the definition of Lorentz transformation is like with constant matrix. Maybe I should have said that. We are always talking about global symmetries, right? So lambda doesn't depend on x. See, normal Lorentz transformation, right? You give a boost or you give a rotation, but it's the same matrix that acts on all space-time points, right? Otherwise, it's not a symmetry typically. See, if lambda had depended on x, right, then you couldn't do what you did here. Because if lambda had an x dependence, right, then this is not true anymore, right? You have to take into account the x dependence of lambda when you do the chain rule. So it's a symmetry of the action only when lambda is independent of x. Lambda is a constant Lorentz matrix.
Okay.
Any other question? Okay. So you have found this. Okay. So you are going to write it again here. So what did you find? So you found this. Okay. No, you didn't find it. Okay. We found this. This is what you have written here. Okay. The same equation that was here. Okay. We wrote here. What is there in this line is our general definition of chi I and k. So how do we define chi I? That we said that under the infinitesimal transformation, phi tilde I and phi I differs by epsilon times chi I. That was the definition of chi I. And similarly, L of phi tilde I del mu phi tilde I and L of phi I del mu phi I should differ by total divergence. Right? This follows from the fact that it's a symmetry of the action. And whatever it's a total divergence of, we call this k. And the idea now is that we compare these. This is the general definition of k mu and chi I with the specific result that we have for Lorentz transformation. This is general for any symmetry. This is for Lorentz transformation, right? We have found what for Lorentz transformation, L of phi tilde del mu phi tilde is given by L of phi del mu phi plus this. So let's compare this with this. What we see that del mu k mu must be this. And that means k mu must be omega mu nu x2 times L. Is this clear? This is what we found for Lorentz transformation. This is what defines k mu. And now all you are saying is that just compare this with this, and that gives you k mu. Any question? Okay. Now we also have this relation, right? This is the way we started with. Phi tilde of x is phi of lambda x. X prime by definition is lambda x. So phi of lambda x was phi of x plus epsilon omega mu nu x to del nu phi. Now compare this with the definition of epsilon phi I. So whatever multiplies epsilon in the definition of the difference between phi tilde and phi is what we have called chi I. So chi of x in this case is just omega mu nu x to del nu phi. Just compare these two. So you have found chi and k for Lorentz, infinitesimal Lorentz transformation. And now the idea is that we will just substitute in the general expression for the Norton current to find J. Is this okay? Okay, so let me proceed. So here I have written the expression for chi and k mu. And now this is the general expression for the conserved current that we had found. And all you have to do is that you have to substitute the expression for chi that we have found for the special case of Lorentz transformation. And we have to substitute for k mu that we have found for the special case of Lorentz transformation. And that gives you this. So this J mu is the conserved current for Lorentz transformation. And notice that this is conserved for every omega. Every omega which comes from an antisymmetric matrix. Okay, so that when both indices are raised or both indices are lowered, it gives an antisymmetric matrix, right? For only every omega of that kind, this is conserved, and that we are going to make use of this in a few minutes. So what we are going to do now, okay, of course, now what we could have done is that we could have taken the expression for L for Klein-Gordon theory, right, and computed this and substituted, right? That will give the expression for J. But we will do something which is a little more compact, and that we are going to do by comparing with the definition of the energy momentum tensor that we had found. So these are the two results that I had reviewed at the beginning of this lecture. So for the energy momentum tensor, what we have found is that we have found the corresponding chi as del rho phi, corresponding k mu as L times delta mu rho, and the corresponding conserved current J mu rho, right? One for every rho, because you have 4 translations. Corresponding conserved current J mu rho was given by this, yeah, which for translation takes this form. So what we are going to do now is that we are going to compare this with what appears here, this expression, to rewrite this in terms of energy momentum. So let's see how you can do that. So this is the claim. Take this expression for J mu, multiply by omega rho nu x nu, you will get this expression. Does everybody see this? First term is omega rho nu x nu times this term. The second term is omega rho nu x nu times this, right? Omega rho nu x nu, so the rho becomes mu, because omega rho nu times delta mu rho becomes omega mu, right? That's what we see here. So what we conclude is that the conserved current for Lorentz transformation, which we have been calling J mu, is given by omega rho nu x nu times J mu rho. The omega rho nu I can just rewrite as eta rho tau times omega tau nu. Okay? That's raising and lowering index. Okay? The reason that I have done that is because now this eta rho tau can be combined with J mu rho to write it as T mu tau. Because you want to write everything in terms of energy momentum tensor. So you get this expression for J mu. And now because omega is antisymmetric, this is not manifestly antisymmetric, but if it has a symmetric part, right, that will just cancel, that will go away, because you have an antisymmetric matrix and symmetric matrix, right, contracted, both indices contracted would have given 0. So I can write this by explicitly antisymmetrizing this and putting a factor of half. So this is our conserved noisy current for rotational symmetry, for Lorentz invariance. Are there questions?
Sir,
Yes.
sir, whether this Lorentz symmetry, the Lorentz transformation, it also includes the space-time translation for the lambda. So the lambda includes also the space-time translation.
No, because space-time translation is a different kind of transformation. So these are independent transformation, right? Because lambda x, right? If you take the point x equal to 0, lambda x will always land you at 0, right? Whereas x going to x plus epsilon moves 0 to another point. So Lorentz transformation and space-time translation are independent symmetries. If they are the same, then of course you would not get independent conserved quantities, right? So they are independent. So total number of symmetries that we have found so far, the total number of continuous symmetries are 4 space-time translation and 6 Lorentz transformation. That's altogether 10. These together sometimes is called Poincare symmetry, but certainly Lorentz symmetry and space-time translation are independent.
Yeah. Okay.
Yeah.
Yeah.
Any other question? So this expression is clear to everybody? Yeah, because this is a key point, right? This is the key derivation of today's lecture, that the expression for the conserved current associated with Lorentz transformation can be rewritten in terms of energy momentum tensor. But of course, it is not the energy momentum tensor, right? Because you have these excludes. Yeah. And now the claim is that because omega tau is an arbitrary antisymmetric matrix, and because this matrix is antisymmetric anyway, for every choice of tau and nu, this must be conserved. Is this clear? So I claim that this is conserved. The fact that this is conserved for every antisymmetric matrix omega means this is conserved. Is this obvious to everybody?
Sir, is this because omega is a constant matrix?
Yeah, omega is an arbitrary constant matrix. Okay.
Yes.
Let's take m mu 0 1. Okay. We want to prove this is conserved. Then take an omega matrix omega, whose 0 1 component is 1. As a result, 1 0 component is minus 1. All the other components 0. So for that matrix, when you substitute it here, you will get m mu 0 1, right? Because that's the only component that will be picked up, right? There will also be minus m mu 1 0, but that's the same as mu 0 1 because m is automatically antisymmetric under the nu tau exchange. So that will tell you that m mu 0 1 is conserved. Similarly, m mu 0 2 is conserved, right? You just choose another omega, right? Whose 0 2 component and 2 0 components are non-zero, everything else is 0. So by choosing these independent omegas, right? So that has only 2 components non-zero at one go, we can prove that m mu nu tau for every nu and tau is independently conserved. That means this equation holds for every nu and tau.
Okay, thank you, sir.
Is this clear to everybody? Now there is this has a consequence. So what is the consequence? It has a consequence that this implies that T mu nu must be symmetric. So let's check that. So we have seen that this is 0. So let's substitute the expression for m mu nu tau, which is here. So you see that this gives you, this is delta nu mu, right? When this acts on T mu tau, that of course is 0 because T mu tau is conserved because translation is also a symmetry. So del mu T mu tau is 0 anyway. Similarly, del mu T mu tau nu is also 0. So two terms which are non-zero, which could be non-zero, are the one where del mu acts on x nu, so that gives you this, and one where del mu acts on x tau, that gives you this. And then after you sum, right, you get T mu tau minus T tau. So this equation then tells us that T mu tau must be equal to T tau. So energy momentum tensor must be symmetric. So this is the consequence. We had seen this earlier. If you remember in the last lecture, we explicitly computed the energy momentum tensor for the Klein-Gordon field, and we expressed surprise that is the symmetric, right? Even though the role that is played by mu and tau index are quite different. But now we see that that symmetry is actually a consequence of rotational invariance or Lorentz invariance. Because the Klein-Gordon field theory is also Lorentz invariant, it had to be symmetric. Now, this again relates to the question that was asked earlier, right? That if we didn't know about Lorentz invariance, right, we could still discover that the energy momentum tensor is symmetric, right? By explicit calculation, we did that. It's just that it would look surprising. Once you have Lorentz invariance, then you see that it's not surprising anymore because it's a consequence of Lorentz invariance. So symmetries can remove some surprises, but you can live without symmetries. You can still work even if you have not discovered certain symmetries. Now, one point I want to emphasize here again is that as long as the Lagrangian is Lorentz invariant, okay, up to this point, right? In this page, for example, we use the fact that Lagrangian is Lorentz invariant. L is Lorentz invariant. That means, or L is Lorentz invariant only in this sense that it transforms by this K mu. But otherwise, we didn't use the explicit form of the Klein-Gordon Lagrangian. So this relation, in fact, is universally valid for all scalar field theories. Even if you have multiple scalars, this is valid. We'll see later that it will not be valid for other kinds of fields which are not scalars, because in this derivation we did use this fact. We did use that the scalars change like this. Okay, we'll see that this is not always true. There are some fields for which there will be extra terms in this transformation. But as long as the fields transform like this, and the Lagrangian density transforms like this as a scalar, our derivation goes through. This relation is universal. Is this okay? Are there questions? Okay, so let me now give some interpretation of these conserved charges, conserved quantities. So you saw that this is conserved current, so del mu of this is 0. So from this, of course, we can consider conserved quantities, which I'll denote by J nu tau, that's by integrating m0 nu tau, right? And for every nu and tau, it's conserved. And because this is antisymmetric in nu and tau, this is also antisymmetric in nu and tau. So you all have altogether 6 conserved quantities, right? Because 4 by 4 matrix, antisymmetric, that's 6 independent matrices. So you have 6 conserved quantities, and that's exactly what we had expected, because Lorentz transformation corresponds to 6 infinitesimal transformations, right? 6 independent infinitesimal transformations. Now let's look at individually Jij, where I and j run from 1 to 3, the space components. So for this takes the form xi times t0j minus xj times t0i. And this now in fact can be given a nice interpretation, because what is t0j? This is the density of j component of momentum. That's what we had found. T0j has the interpretation that this is the density of jth component of momentum. So what you see here is that this is the angular momentum, or what we call orbital angular momentum, for the jth, this is the density of angular momentum, right? Because xi pj minus xj pi is the angular momentum, right? x1 p2 minus x2 p3, sorry, x1 p2 minus x2 p1 is the angular momentum in the third direction, right? And so on. So x2 p3 minus x2 p3 minus x3 p2 is the angular momentum in the one direction, right? And so on. So xi times the density of angular momentum in the jth direction minus xj times the density of angular momentum in the ith direction has the interpretation of the angular momentum density. So its integral should correspond to the total angular momentum. Is this clear? So there are 3 of these, right? Because these are 3 by 3 antisymmetric matrix, and these represent the 3 independent components of angular momentum of the system. Any question? This one is more unfamiliar. J0i. J0i here is the integral of m00i. So this is integral dq bar x0 times t0i minus x sine times t00. So these are the conserved quantities that are associated with the Lorentz boost. Now the fact that these are conserved, that there is no doubt about, right? Because North's theorem told us that this should be conserved, and these are conserved. But what is a little peculiar about these conserved quantities is that they have explicit time dependence, right? X0 is time. So their construction uses time explicitly. And these are the conserved quantities associated with Lorentz boost. Now normally we don't see this. Okay, we don't talk about this very much. Okay, these kinds of conserved quantities, and the reason is the following: that because these have explicit time dependence, so in the quantum theory, these will not commute to the Hamiltonian. These conserved quantities, when you make this into a quantum system, these will not commute to the Hamiltonian. Unlike these, these generators, dj dt equal to 0, ddt of gij equal to 0 would mean that these will commute to the Hamiltonian. But these will not commute to the Hamiltonian, because after all, what is ddt of j0i? This is a general expression, right? There is a commutator with the Hamiltonian, but if this has an explicit time dependence built in, then you should also have that partial derivative with respect to time, right? Where the explicit time dependence is taken into account. These ones don't. These ones don't have explicit time dependence. As you can see, they have explicit space dependent terms, but not time dependent. So they commute to the Hamiltonian. But this one doesn't. And as a result, this is non-zero. That means that you cannot simultaneously diagonalize the Hamiltonian and these conserved quantities. And this simply reflects the fact that if we make a Lorentz boost, then the energy of the particle doesn't remain unchanged. Right? The energy of a particle changes. That you know, right? If a particle is at rest, its energy is m. Okay, let me go back to that. I don't have to go back. I think E equal to square root of p square plus m square, right? You can always remember that formula, right? So if you start with a particle at p equal to 0, then E is m. Now you give it a boost, right? M of course remains the same, but the momentum is non-zero now. So the energy changes. So Lorentz boost corresponds to a symmetry. It gives rise to conserved charge according to Lorentz theorem, but it actually doesn't commute to the Hamiltonian. So it acting on a given system, it changes the energy of the system. Nevertheless, it's very useful because having this conserved charge or the associated symmetry built in tells us that we can actually make use of these in analyzing quantum field theories. Again, let me emphasize that nothing you can do with symmetries, you cannot do without symmetries. If you didn't discover these symmetries, right, you would still be able to do quantum field theory. It's just that the analysis will become much more complicated, right, because you will not be able to use many of the tools that the symmetry gives you. So that will be the role of symmetries that we will see in our analysis. Are there questions?
Sir?
Yes.
Sir, this J0i quantity, it's a conserved quantity from Noether's procedure.
Yes.
Okay, because it's not commuting with the Hamiltonian, we cannot say that it's sensible in QFT.
No, it's
Am I
sensible
right?
in QFT. We'll see that it's sensible in QFT, and that's all the Green's functions will be invariant on a Lorentz transformation. But it doesn't commute to the Hamiltonian.
Okay.
Right?
Okay. So if it's a conserved quantity in in a classical sense, then what does it correspond to?
Yeah. So it will also be conserved in a quantum sense. This is still true in quantum sense. as long as the theory doesn't have anomaly, right? We say that some symmetries can be classically real but not quantum mechanically, but as long as this symmetry is quantum mechanically real, there will still be conserved quantity in quantum mechanics. Right? So this is a quantum equation. But it's just not, it doesn't mean that it commutes with the Hamiltonian.
Okay. Okay.
Right? So it's not that this is only classical conserved quantity and not quantum conserved quantity. This is as good a conserved quantity as these ones, the GIJs.
Okay.
GIJs, for example, doesn't commute to the space transition, right? Okay, because the xi, there is explicit xi sitting here, and that you can show implies that it doesn't commute to the space transition. But which is okay, right? And we know that because if we start with a particle in a given momentum, right? Then once you make a rotation, the momentum changes. So that means the JIJs don't commute to the transition generators, okay, the space transition generators. In the same spirit, J0Is don't commute to the time transition generator, which is the Hamiltonian in this case.
Okay, sir. Thank you.
Any other question? Okay, so then I'll stop here today. So tomorrow we'll be discussing.
Sir?
Yes.
Sir, I was small doubt in page number 102.
102, okay.
Yes, sir.
Yes.
Sir, I don't understand it why we are taking omega mu nu x nu inside the derivative in the Lagrangian density expression. Yeah, this. Yeah.
Oh, here?
Yeah, this, sir.
This one?
Yeah, yes, sir.
See, this one came from the last slide here.
Yeah.
This. At this to begin with, right?
Yes, sir.
We said, so let's look at the difference between this and this. The difference will involve when this partial derivative acts on x nu, right? Omega is constant, right? So when you calculate this, right, there will be one term which is omega mu nu x nu times del mu, right? That's this term. But there will also be another term where it's omega mu nu times del mu x nu, right? Because this is by chain rule of differentiation, by distribution property, right?
Okay.
So this term is x term, right? But this term, right, I manipulated. I said that this is omega mu nu, del mu x nu is just delta nu. Then I
understood.
And this gave you 0.
Understood. Yes, sir. Understood.
So the extra term just vanishes. That's how you could take the del mu out.
Understood. Yes, sir.
Okay. Any other question? Okay, so tomorrow then we'll be dealing with fields which are not scalars. And we'll see how to deal with those. So I think for today I'll stop here.